Oh, here we go. Here we go. The sixth lesson of the chapter, and this is section 3.5. I would say this is a tough but easy day. Tough in that you got to pay attention to get the concept, but once you get the concept, it's pretty straightforward. Well, unfortunately, we're moving on from triangles, but don't worry, we'll come back to triangles. Don't worry, triangle, don't cry. All right. Remember, we're talking about polygons. Polygons are closed plane figures consisting of segments that join at their endpoints. Poly meaning many, and gon meaning angle or corner, so many angles. There are a few rules. Remember, to be a polygon, first off, the sides have to be segments. So that's a polygon, but that isn't a polygon. Why? Because one of the sides is a curve. They also have to be segments joined at their endpoints. So yes, that's a polygon, but no. Notice two of those sides are not joined at their endpoints. And then all the intersections have to happen at the endpoints. So even though I'm joining each segment at their endpoints there, I have an intersection that happens kind of in the middle. So that one also is not a polygon. All right. There are some complicated rules, right? Here's a complicated rule. Now, remember I said it was a tough but easy day, so pay attention to this definition. So let's say I have a polygon. Look, there's segments joined at their endpoints, and I pick two random points inside the polygon and play connect the dots. Notice no matter what 2 points I pick, the red line is never outside of the shape. Contrast that with this polygon. I'm still made up of segments joined at their endpoints, but check this out. I can select 2 points that when I play connect the dots, the red line actually goes outside of the shape. In other words, it intersects the side of the polygon. These two shapes are two different types of polygons. The first one is called a convex polygon. And a convex polygon is when I select any 2 points at random, right? The line drawn between those 2 points will always be inside the polygon. The second type is called a concave polygon. And a concave polygon is one where I can select 2 points that when I play connect the dots, look, the red line is outside of the polygon at some locations. It's not always inside, sometimes it's outside. Okay, so there's your first two complicated definitions for polygons. All right, there are other types of polygons, and these are the ones that you're more familiar with. So these are the ones you have to either have your book of truth or memorized. If we start with three-sided polygon, we call that a triangle. I'm going to do this very quickly, but remember you can pause. A four-sided polygon is called a quadrilateral. Quad meaning four, lateral meaning sides. A five-sided is called a pentagon, penta for five, gon for angles. Six-sided is called a hexagon, hex is six, gon is angles, six angles. Seven is either called a septagon or a heptagon, so our book uses heptagon. Eight is a stop sign. We call those octagons, eight angles. Nine is called a nonagon. And lastly, we'll stop at 10 and we'll call 10, since it has 10 sides, a decagon. Decade, 10, right? Decagon. Oh, I left one out. All right. What happens if I have an unknown number of sides? So I'm going to let the letter N represent how many sides. Therefore, what would you call this polygon if it had N sides? Well, if I follow the pattern there, that would be called an N-gon. All right, make sure you have all those written down, either memorized or written in your book of truth. We'll get to the test day and it'll say something like you have a decagon, and if you forget that it has 10 sides, you can't answer the question. All right. Well, we know how to name triangles. You pick a corner, you go clockwise or counterclockwise. So we'll do the same thing with all polygons. Pick a corner, any corner, stay on a black line, and either go clockwise or counterclockwise. So if we start with A and go clockwise, that would be A, B, C, D. If we go counterclockwise, that would be A, or start with C, that would be C, B, A, D. All right, we'll stop at quadrilaterals. We don't want to do a decagon and give its name, but it would be all 10 sides. All right. Now it's time to turn our brains. We're going to get formulas, a couple formulas. All right. Let's talk about the vertices of a polygon. Those vertices correspond with interior angles. Each one of those is an interior angle of this polygon. And if I were to ask you what would happen if you added up all of those angles, what would the answer be? And then the second follow-on question, would it be the same as for a hexagon or a quadrilateral? Would the sum of the interior angles be different? Well, we know what the sum of the interior angles is for a triangle. It's 180. We proved that. So now we're going to prove what it is for all the other polygons. I mean all of them, an infinite number of ones. All right. So in order to answer this question, what's the sum of the interior angles of a polygon? I need you to think about this. Okay? Think about what would it mean to join non-consecutive vertices, non-consecutive corners. So if I were to join non-consecutive corners, that means pick a corner and then join it with any corner that's not next to it. Well, there's only one, that one. What we just made right there by definition is what we're going to call a diagonal. And I don't have you actually write this down. Most of the kids can remember this one. That's called a diagonal, right? Diagonals are an auxiliary line, so therefore they're represented by a red dashed or dotted line. It turns out that making diagonals is going to allow us to get to the answer of what is the sum of the interior angles of a polygon. So check this out. I have three different shapes there, three different polygons. If I choose one corner of my quadrilateral and create as many diagonals as I can, just one corner, well, that would only be one. And notice what they did when I did that. It broke it up into two different triangles. So let me write down some data. So if you have four sides of a polygon and you make a diagonal, you wind up with two triangles. All right, let's go to the next shape. Pick a corner, any corner. Make the diagonals. Well, there would be one there and one there. Remember, we can only connect non-consecutive vertices. Well, that would be three triangles, but this one had five sides. Lastly, the hexagon right there, pick one corner, any corner. Make the diagonals, 1, 2, 3. So that would be six sides. Oh, I'm sorry, I counted wrong for triangles. There's four of them. Four triangles, 1, 2, 3, 4. Do you notice that there's a pattern there? Four sides has two triangles. Five sides has three triangles. Six sides has four triangles. Notice that the number of sides and the number of triangles are related if we subtract 2. So if n is the number of sides of a polygon, how many triangles will it have? It will have n minus 2 triangles, where n is the number of sides and n minus 2 is the number of triangles that you make by creating those diagonals, right? So there's n minus 2 triangles. Quadrilaterals have two triangles. 5 minus 3 is 2, so you have 5 minus 2 is 3. There we go, I said it right. So you have three triangles for the pentagon, and 6 minus 2 is 4, so you have four triangles for the hexagon. All right, well, we'll recall that the sum of the interior angles of a triangle is 180. We've proven that. That's theorem 311. So let's apply that to what we just did. If n is the number of sides, and n minus 2 is the number of triangles that you make, and every triangle has 180 degrees, right? So it would be n minus 2 times 180, which would be the sum of the interior angles of any polygon. So quadrilateral has four sides. 4 minus 2 is 2. 2 times 180 is 360. So the sum of the interior angles of a quadrilateral, that could be a square, rectangle, rhombus, any of those, would be 360. Sum of the interior angles of a pentagon would be a 5 minus 2 or 3 times 180. That would be 540 degrees. And the sum of a hexagon would be 6 minus 2 is 4. 4 times 180 is 720. So to answer the question, do the sum of the interior angles stay the same, or does it change as the number of sides goes up? It goes up. So theorem 313 gives us the formula to calculate the sum of the interior angles of a triangle. It's just n minus 2 times 180, where n is the number of sides. Okay. So for my pentagon, this is just one example. 5 times 2 is 3. 3 times 180 is 540. Believe it or not, for homework, they're going to give you a shape and say, what's the sum of the interior angles? Well, count the number of sides, 6. Plug in 6 for n, do the math, 720. Cool? All right. Where to now? Well, let's think about exterior angles now. So for exterior angles, right, think about this. If I were to draw auxiliary lines, extend each side, I would get to those exterior angles. There, Each one would be 90 degrees. Well, that would be easy to add up. 90 plus 90 plus 90 is 360. But what would happen for the pentagon? What would happen for the hexagon? Well, let's explore that. Boy, is this a slick proof. I love this proof. All right, let's look at one of those angles. One of those angles is made up of an exterior angle and an interior angle. And look, if you put both of those angles together, 1 and 2, well, 1 and 2, you get a line, right? So if I took the sum of one of those points right there, the one I just did in red, times the number of sides, right? So the sum of one interior angle plus the sum of one exterior angle, that has to equal 180. So the sum of all the interior angles, we know a formula for that. That's n minus 2 times 180. The sum of one exterior angle, I don't know what that answer is, times how many sides it has, that would be n, that would be our formula. So let's plug what we know. All the interior angles, we know that formula, n minus 2 times 180. I don't know the sum of all exterior angles. We'll call it x. But I do know if I multiply 180 times n, that will be the answer. Now watch this slick, right? Do the distributive property there. 180 times n is 180n. 180 times 2 is negative 360 or minus 360. And look what happens. I got a 180n on both sides of the equation. Subtract that. Now add 360 and it says x. Well, what was x? X was the sum of all exterior angles. So for interior angles, it's n minus 2 times 180. But for exterior angles, there's not a formula there. There's just a number. That means for all polygons, the sum of the exterior angles is 360. Well, that's not a formula. That's just a number. That makes our life easy, actually. So 314, or theorem 314 says the sum of all the exterior angles is 360 degrees. No formula necessary. Okay. Quick example. What's the sum of the exterior angles of a hexagon? Well, it's 360. There's no math. What's the sum of the exterior of any polygon? It's 360. Boy, that was easy. So we've done two skills so far, interior, exterior. Interior is an actual formula and represents the number of sides. And for exterior, the answer is always 360. Are there different types of polygons? Sure are, right? Let's see, we have equilateral polygons. Equilateral polygons where all the sides are the same. I'm going to do this quickly. You can pause and write these down. We have equiangular polygons where all the angles are the same. And then a combination of both is called a regular polygon. That's where all the sides have the same number and all the angles have the same number. Doesn't mean the sides equal the angle, right? The number, like it's not, we're saying the side there isn't 120 centimeters. The side could be any distance, but the angles are all 120. And that's for this one, a regular hexagon. So now it gets slightly challenging, right? We're just going to add some complexity to our formulas. So notice what it's asking there. It says not what's the sum of the interior angles of the polygon, right? That would be n minus 2 times 180, right? The question I'm going to ask is, what is the sum of the exterior angles of a pentagon? Well, that's just 360. But what I'm going to ask you is one angle. Here's what I'm asking you. I'm saying, what is the value of one interior angle of a regular polygon? It doesn't say one, it says an, but that's what it means. What is the value of an interior angle of a regular polygon? It means I need one of them. So if the sum of the interior angles of a pentagon is 540, I just need to divide 540 by how many sides there are. Because remember, all the sides equal the same for a regular pentagon. Well, 540 divided by 5 is 108. What about one exterior angle? Once again, all the exterior angles add up to 360. So if I want one, just divide by 5. Well, this would lead us to a formula. One more example, real quick. How about a hexagon? So the sum of the interior angles of a hexagon, that's n minus 2 times 180, 720. Exterior angles always add up to 360, but how about one interior angle? Well, that would take the sum of the interior angles, which is 720, and divide by 6. That would be 120 degrees. And one exterior angle, that would be 60 degrees. So this leads us to that formula. Here's all 4 of them on one page. The sum of the interior angles is n minus 2 times 180. The sum of all the exterior angles is 360. Not much of a formula there. The value of one interior angle would be n minus 2 times 180 divided by how many sides, and that would be n. All right, that's a little bit more challenging of a formula. And then lastly, one exterior angle will be 360 divided by n. So these are the four formulas that you need in order to do your homework. Okay, that's where this lesson comes to an end. So once again, here's your homework. And as always, see me in the hallway. Send me an email if you need help. And I'll see you in the last lesson. One more to go.